In part 4 of module 4, we're going to be looking at the transient process and how we can apply the first law for open system for transient processes. So we had given examples earlier about transient processes. So for example, filling up a bathtub or emptying a bathtub or filling up a piston cylinder device. Those are all examples of transient processes. And for the transient process, we need to solve the continuity equation in the first law with an extra term that we had canceled for the steady process. So let's look at the continuity equation first, which is our conservation of mass equation. And we can say that now the continuity equation for a transient process where we have a change in mass inside a control volume would be the following. We would have essentially the integral of the sum of the mass flow rate in minus the integral of the sum of the mass flow rates out would be equal to the change in mass with time all integrated from point 1 to point 2 in terms of time. Okay, and what that really means is that if we have a difference between the mass flow rate in and the mass flow rate out, we're therefore going to get a change in mass over time in our control volume. Just like if we look at time 1 at 0 seconds and time 2 at 60 seconds, if we're filling up a sink, you would fill up the sink and you would change the mass of the water in the sink throughout the 60 seconds. Okay, so we can rewrite this equation. If we compute the integrals, we can say that the sum of the mass in, so not mass flow rate, but total mass, minus the sum of the mass out is equal to mass 2 minus mass 1 of the control volume. And the 1 and the 2 refers to times, okay? So it's times 1 and 2, not necessarily positions. So we can rewrite this equation. If we want to, we can just rearrange it to say that M2 minus M1 inside the control volume, so the mass at time 2 and the mass at time 1 subtracted, plus the sum of the mass out minus the sum of the mass in is equal to 0. And this will become clear how we can apply this to an example problem that we're going to be doing in this section. Now, if we now look at the first law for open systems and we go back to our general definition for our first law for open systems, we can write, we had written that Q dot in minus work dot out is equal to the change in energy within the control volume over dt over time. Okay, now we don't have a steady flow, but we have a transient flow, so we need to keep this term, and we need to keep this term because the mass changes inside the system. Okay, so we're going to write the rest of the equation, which is our typical equation due to flow at the boundary. So we have sum of m dot exit times HE plus V exit squared over 2 plus GZ E minus the sum of the mass flow rates in times HI plus VI squared over 2 plus GZI. And we can break down this equation to say this term here, these two terms here, are due to the flow at the boundary. Okay, just like in our steady system, due to flow in boundary. Now, the first term here is actually due to the mass change. So it's because mass changes. And we can write that the mass changes inside the system with time. And that's what this term is essentially taking into account. And the mass can change positively if we're adding mass to the system, but it can also change negatively if we're taking out mass of the system. If we have a transient process and we're told that we have a transient process, or we have added mass or taking out mass of a system, we immediately know we do not have a steady flow system, we do not have a steady state system, but we have a transient system. And this dE control volume over dt can be written as the change with time of the energy inside the control volume. So what is the energy inside the control volume? Well, the energy inside the control volume is mass times the internal energy plus the kinetic energy term plus G Z. So this is the information for the inside of our system. Now, the velocity here is not the velocity at the exit or at the inlet. It's the velocity inside the system, if there is any. Okay, and now what we can do is we can say that if we integrate both sides, we have that the energy of the control volume is essentially m times u plus 1/2 v squared plus gz. If we want to write it in full form in a simpler way, we can say that it's capital U plus KE plus PE at a given moment in time. Now, if we integrate this equation from time 1 to time 2 and this equation from time 1 to time 2, we actually get that the change in energy of the control volume between time 1 and time 2 is equal to m2 times u2 plus 1/2 v2 squared plus gz2 minus m1 times u1 plus 1/2 v1 squared plus gz. And again, the term 1 and 2 are time terms. Okay, so that's very important. So now what we can do is we can write the full transient equation now that we have a term for dECV dt. Okay, so we have this term and we can now plug into our equation for time 1 to 2 and for the inlet and exit. So if we have an open system with two different times, we're going to get the following equation. We're going to get that Q in minus work out is equal to the sum of the mass exiting times HE plus 1/2 VE squared plus GZE minus the sum of the masses in times H in plus 1/2 V in squared plus GZI plus, I'm going to write it under here, plus M2 times U2 plus V2 squared over 2 plus GZ2 minus M1 U1 plus V1 squared over 2 plus GZ1, all close bracket, and that gives us our equation. Okay, so our equation is kind of long and it looks very complicated, but it's actually pretty simple to use. So we can define this as our transient equation for open systems. And I'm going to highlight some parts of this transient equation so that we can understand within a system what it means. So let's say that we have a system that looks something like this. We have a piston cylinder device, just to keep it simple, and we're going to have an opening here, an opening here, and we're going to have some work going out of the system. We're going to have some Q into the system, and we're going to have a change in mass between time equals 0 and time equals 60 seconds. Okay, so we have all this information. And if we break down our system and we look at this part being the part at the boundaries and the part below it being the part inside the flow, we can call this, for example, little a, little b, and we can say this is little c and d. We can now say that A is, for example, associated with the exit of the flow. So the flow would be exiting this way and coming into this one. We can say that A is located right here. We can say that B is located at the entrance. So that's where we would find our expression for B. And then C would be associated with the mass in the system at time 0 and the temperature in the system at time 0, and all the rest of the information like pressure and specific volume and internal energy. And then D would be the same system at time equals 60 seconds. So kind of like state 1, state 2. So C would be state 1, D would be state 2, and those are time states. And then A and B would be state E for A, and for B we would have state I for the entrance of our system. And obviously we can have multiple entrances, multiple exits, but in a simple system we would usually only have one entry, one exit, or something a little bit simpler. So the next thing we're going to be doing is trying to apply this equation to a pretty simple problem to sort of understand how we can apply it to a transient system where we have a change in mass within the system. So I'm going to copy over an example problem from your handout, and we're going to be doing it together now. So we are told that a piston cylinder device initially contains 0.6 kilograms of steam. So we know that it initially contains, so that's probably state 1, contains 0.6 kilograms of steam with a volume of 0.1 meters cubed. The mass of the piston is such that it maintains a constant pressure of 800 kilopascals. So a very simple piston cylinder assembly with a piston that keeps a pressure constant. So we can say that the pressure is constant throughout. And we're told that the cylinder is connected through a valve supply line that carries steam at 5 megapascals and 500 degrees Celsius. Now the valve is opened and the steam is allowed to flow slowly into the cylinder until the volume of the cylinder doubles and the temperature in the cylinder reaches 250 degrees. So essentially our state 1 is defined at the top. This is our state I essentially. Okay, it's our inlet state, and we're told that at time 0 the inlet is closed. So we can say at time 0 valve is closed. And then at some point we open the valve until at time 2 we have that V2 is equal to 2 times the volume of 1. Okay, so this would define our state 2 essentially, this sentence right here. So let's try and write all of our states for our system so that it makes sense. And how I like to start these problems is to just write all the states to have all the information in one place and figure out what we have. So what we do is we count all the inlets, all the exits, and all the time changes. So there's only 2 time changes here, and there's 1 inlet and there's no exit. So we're going to write state 1, state 2, which are time states, then state I, and state E. Now, as we can see in our system, we already know, let me just underline them all, we already know that state E doesn't exist. We don't have an exit term. So we can get rid of state E. We know that there is no state E. So we're left with 3 states. Okay? Our first state, we're given the information that mass 1 is equal to 0.6 kilograms. Then we have V1 is equal to 0.1 meters cubed. Okay, that's our volume 1. And we're also told that pressure 1 is equal to 800 kilopascals due to the fact that the piston keeps a constant pressure in our system all the time. In state 2, since the pressure is always constant, we can say that pressure 2 is equal to 800 kilopascals still. It's equal to pressure 1. We know that V2 has to be equal to double V1, so we have 0.2 meters cubed. And we're also told that temperature 2 is 250 degrees Celsius. 250 degrees Celsius. So that's the information we're given. Okay, so in state 1, we're not given any temperature. In state 2, we are given temperature, but we're not given mass. Now, at state I, at the inlet, we're told that we have steam coming in at a pressure I equal to 5,000 kilopascals or 5 megapascals. Okay? And we're told that Ti is equal to 500 degrees Celsius. So that's the temperature and pressure of our water coming into our system. So now what we can do is we can apply our continuity in our first law equation to this type of problem. So the first thing we can say is that, let's look at continuity. So the continuity equation says that we have Mi, the mass in, is going to be equal to mass 2 minus mass 1. Okay, it makes sense. The mass of flow coming in is going to be equal to the difference between mass 2 and mass 1. Okay, you can think of it in a different way where if you say mass 1 plus the mass coming in would be equal to the mass at time 2. Okay, so we have this first equation for continuity. And right now we only know our mass 1. We don't really know anything else. Okay, now we can then apply the first law equation. And some of the assumptions we can make for our first law is that we're not given any kinetic energy or potential energy equations for the system as well as the boundaries. So sometimes you might be given a velocity at the boundary, so you have to take into account kinetic energy at the boundary. Here there is no change in kinetic energy at the boundary and for the system itself inside. Okay, nothing is moving inside the system. Okay, so we can say that delta KE is equal to 0 and delta PE is equal to 0 for the system and boundaries. So moving forward from that, we can simplify our whole equation a little bit more. So we're going to be using this full equation at the top here, the full transient equation, and writing it out. So we have, if we simplify it without the velocity terms and the kinetic energy term and the potential energy term, we have that Q in minus work out is equal to the mass at the exit times HE minus the mass at the inlet times HI plus M2 U2 minus M1 U1. Okay, and notice how I decided to use the equation without our Q dot and W dot. So if you notice in our transient equation, I did not use Q dot and W dot. I could also use Q dot and W dot, but usually when you have a transient system, you want to use your actual values for work and heat in, not your rate values. But sometimes you'll have to use your rate values. So you can use both equations, but for the transient process, we usually use non-rate values, so without the dots at the top. Okay, just making sure that that's clear. So we have this equation, and we now need to figure out what is happening. So the first thing we can do is we can cancel ME, HE because we don't have any mass exiting the system. We only have mass coming into the system. So we can say that Q in minus work out is equal to M2U2 minus M1U1 minus MI HI. Okay, so we have this equation, and now the first thing we need to figure out is all the terms to look at what we need to figure out in the question. So now that we have our first law set up and we have our continuity set up, let's look at what the question is asking. So the question asks, determine the mass of steam that has entered and the amount of heat transfer. So we're going to be looking at two different things. We're looking for MI, so we're looking for MI, which is in these two places, and we're also looking for the heat in, which is this term right here. So we have two equations, two unknowns, so we should be able to figure out what is happening. Okay, so how do we solve this problem? Well, the first thing we can find is we need to find all the other terms in the equation in order to find MI, most probably. Okay, so we have, I'm just going to draw this first equation here, and then we have a second equation that says that MI is equal to M2 minus M1. So if we can figure out M2, we already know mass 1. If we can figure out M2, we can find MI. So how are we going to do this? Well, we know that at state 2, we know that we have, so let's look for MI first. So part A says to find MI. So we know that we need to find M2 to find MI. And M2 is at state 2. So let's try and figure out at state 2 if we can find mass 2. So at state 2, we're given pressure, volume, and temperature. Okay, so we have pressure, volume, and temperature. So how are we able to find mass? Well, the definition of mass is actually equal to the following. We can say that M2 is equal to volume 2 over specific volume 2. And that comes from the fact that mass is equal to density times volume 2. Okay, so M2 is equal to density 2 times volume 2. But we can use the specific volume methodology. So if we can find specific volume 2, then we can solve for M2, and finally we can find MI. So how do we find specific volume 2? We know we have water in our system. So if we have water, we're going to use tables. And in our tables, to find V2, we're given that pressure 2 is equal to 800 kilopascals and temperature 2 is equal to 250 degrees Celsius. So we can say from our tables that V2 is going to be equal to, and I'll go to our tables now just to show you how to do it. So we have pressure and temperature, so we go to the pressure table, we go to 800, and at 800 we see that our saturation temperature is 170. So that means that T is greater than Tsat, so it's superheated. And since it's superheated, we can go to table A6, where we have our superheated data. We go to 0.8, and we're going to go to a different temperature that's shown right here. So we're going to go to 250 degrees for this problem. And we see that at 250 degrees, we have a V2 that is equal to 0.29321. Now, at this point, there are two things you can do. So you can either fill your system with all the information you need to know, or go step by step. So you know that you're also going to have to find, at some point, you're going to have to find U2. And since you're already at state 2, you might as well write U2 at that point as well, so that you have it already, since you're already at your tables. So to sort of shortcut our system to find Q in part B, we're actually going to write down U2 as well. And U2 going to our tables is equal to 2,715.9 kilojoules per kilogram. Okay, so it's a little bit of a shortcut. We know that in part B we're looking for Q, therefore we know that we need U2, and we can find U2 from our tables directly. Okay, so now that we have specific volume 2, we can say that mass 2 is equal to V2 over specific volume 2, which is equal to 0.6821 kilograms. Okay, once you do the math. And now we can find Mi is equal to M2 minus M1 from continuity, which if we do 0.6821 minus 0.6, which is M1, we get that this is equal to 0.0821 kilograms. So that's the change in mass over time in our system, our mass coming into our system. Now for part B, we need to find Q in. And Q into our system is equal to work out plus M2U2 minus M1U1 minus MIHI. So now we already have M2, U2, we have M1, we have MI. What we're left to find is we have to find W out, we have to find U1 and HI. Okay, so those are the three terms that we have to find. So let's look for U1 first. So at state 1, we have that pressure 1 is equal to 800 kilopascals. And we have a second term that we can find at state 1, it's our specific volume. So we can find our specific volume so that we can use our tables. Our specific volume is just the volume over mass. We're given volume, we're given mass. Therefore, we can say that the specific volume is equal to 0.16667 meters cubed per kilogram. And from here, we can figure out in our tables what our term is. So using the tables, we can go to our tables. We go to table A5 once again, we're at 800 kilopascals. And we see that, so just to erase here what we have, we can see that at 800, we're going to verify where our VF lies. And we can see that our V lies between VF and VG. So VF is less than V, which is less than VG. So it's between the two. So we know we have a saturated mix. And since we know the value, we can find X. So I'm not going to go through the process, but I'll let you do this on your own. So we can find what X is equal to. And then once we find the X, we can then find the equivalent U from U1 is equal to UF times 1 minus X plus UG times X. And we get that U1 is equal to 2004.4 kilojoules per kilogram. Okay, and I'll let you do this in your own time because you should have enough training to be able to find values from your tables. So that's our state 1. So now we have U1. We're good to go with U1. So now let's try and find H1. HI, sorry, not H1. So HI, you can get from tables as well. And for the inlet state, we have the following things. We have that Pi is equal to 5,000 kilopascals and Ti is equal to 500 degrees Celsius. So from there, we can go to our tables once again and look for 5 megapascals and 500 degrees. So we can start with our pressure table. We go to 5 megapascals, which is right here. So let me erase 4,000. So at 5,000, we have a Tsat of 263. Clearly, our temperature is higher than that, so we have a superheated vapor. And following that, we can go to our table A6, where we have 5 megapascals, which is shown right here on the box here. Okay, in this box right here. And we can look for 500 degrees Celsius, where we would find that HI is equal to 3434.7. So HI from tables is equal to 3434.7 kilojoules per kilogram. So now we have the value for HI. The only thing left is the work out. So how do we find the work out when we have a piston cylinder? Well, we know that it's the integral of PdV. And in this case, we have a constant pressure, so it's just going to be the area under the curve. And our process is going to look something like this. So we have our pressure, our volume, and we're just going to go from point 1 to point 2, where we increase our volume. And we have our value at volume 1, we have our value at volume 2, and we have our pressure constant of 800 kilopascals. And so we can just write that the area under the curve, the work out, is equal to pressure minus 0 times V2 minus V1. And that is equal to 800 multiplied by 0.2 minus 0.1. The volumes are given in the question directly. So we have 80 kilojoules of work, positive work. Okay, we're going from 1 to 2. So now we have all the terms. We can just add them all together, multiply them all together, just follow the equation, and we get that Qin is equal to 448 kilojoules. And so we've answered part B of our problem by answering the heat change. So part B of our problem said the amount of heat transfer. So we've shown the amount of heat transfer. So this concludes Module 4. In Module 5, we're going to be introducing the second law of thermodynamics and see how it relates with the first law. So see you in Module 5.